The next section of this chapter and of our class will focus on, once we have done measurements, how can we compare them? If we have, say, two different measurements of a sample or two different samples, do we know if they're the same or if they're different within the errors that we've estimated for them? And so the first thing that we're going to talk about to be able to make comparisons valid is the idea of a confidence interval. So this is related to the idea of a standard deviation, but a standard deviation only works if we have an infinite amount of data. So if we know the whole Gaussian curve for a set of measurements, and we know the standard deviation, we can decide what exact percentage of time we can take the area under the curve, find the exact percentage of time that a measurement will fit into a specific interval. But in the absence of actually having an infinite amount of data and the full description of the Gaussian, we only have our sample standard deviation and mean. So our sample mean, again, we write as x bar, and our sample standard deviation we write as lowercase s. And these are just approximations to the population standard deviation and the population mean. So the way we can bridge this gap is we introduce the variable or the concept known as student's t. Now student is a pseudonym for a Scotsman or an Irishman. I can't remember which now. He actually worked for a brewing company and came up with these statistical analysis tools. W.S. Gossett was his actual name. So student here is not as in like it's a student was just his nickname, his pseudonym that he published under. He published these statistical ideas. We use student's t, which allows us to estimate what the actual spread, it allows us to bridge that gap between the fact that we don't have infinite data, but we'd like to be able to know what percent of time we'd expect a measurement to fit a specific interval. So for a regular sample size, we use student's t, and the confidence interval relies on student's t. So the confidence interval is given by this equation. It's equal to the sample mean plus or minus student's t times the sample standard deviation divided by the square root of the number of measurements. We sometimes rewrite this as x bar plus or minus t times ux, where ux is equal to the standard deviation of the mean. Now the question is, we know how to find a mean, we know how to find standard deviation, we know the number of measurements we've taken. So the big question is, how do we know what value to use for t, student's t here? And to do this, we can calculate this, or the easier way is we can look it up in a table. So let me switch over to PowerPoint here. And this is a table from your textbook. This is table 4.4. I'm going to make this full screen. And these are different values of student's t. And you see there's a lot of different possible values here. So on the left, the values are listed by degrees of freedom. So for a measurement of several samples that we've averaged, in general, the degrees of freedom will be the number of measurements minus 1. So if we have, say, 8 values that we've measured, we would look up the 7 degrees of freedom entry. Sometimes we'll have cases where we have, something different than that, but for most cases, it'll be the number of measurements minus 1. And then across the top, we have different confidence levels. And so these represent the confidence that we have, what range, the range that we calculate, what's the percent time that we would expect one of our measurements, that we would expect the true mean to lie within this range. The confidence level that we mostly use in analytical chemistry is the 95% confidence level, but we can see you can put in arbitrary confidence levels if you want. but we generally use the 95% confidence level. So that's why that's highlighted in blue, and that's mostly what we'll use, though we will do occasionally some calculations with other things.